I think you are seeing the numbers, and those numbers are probably translating into people you know, not statistic ones, but also the numbers of the people who are dying is also increasing as is to be expected. As I've mentioned, this particular member of staff, it just took 10 days, and typically that's how much it takes. So it doesn't take a lot of days for COVID to kill someone. So please continue to look after yourself, wear those masks, and hopefully, maybe, I don't know, this thing will pass over us. So yes, we lost someone yesterday, very close to us. We still have another member of staff who is sick, so we don't know exactly what's happening that side. Just a minute. I don't know why things are not working. Oh. Okay. Can you see my screen? Are you able to see my screen?
Yes, sir. No, sir.
There is no and yes. What else are you having?
We cannot see it, sir. There's no screen.
Are people able to see my screen? Can you see?
No, sir.
Just give it a minute.
No, sir.
No?
No, sir.
Hey. No? Still no?
There's only your peak on the screen.
Okay, just a minute. How about now?
Only the peak still.
Are we able to see?
No, sir.
How do we solve this? Okay, let me see. Okay, I need to try something else. Just a minute. Just a minute. How about now? Can you see?
No, sir, I can't see.
How do we do this now? We'll have to wait a bit because I'm trying to do whatever it is I can do, but things seem to be taking longer. Can we see?
Yes, sir.
Yes.
Okay, fine. All right, so today I think we're going to look at 2 examples. Then we'll conclude this thing tomorrow. Then after that, I can hand you over to the other professor who's going to be taking starting next week. So, the example we want to look at today is example number 4. And example number 4 involves trains, 2 train cars which get attached to each other after they collide. So this example number 4 is, of course, it's an application of conservation of linear momentum. And there are certain things which you're supposed to be aware of when it comes to conservation of linear momentum. We make some assumptions when we talk about conservation of linear momentum. The first one is that these particular objects which are involved in this collision, they are moving at constant velocity. So there is no force which is present, there is no external force which is acting on these objects, and that external force which is not, there is no external force to cause the velocity of these particular objects to change. So we assume that these objects always move at constant velocity up to just before the collision happens and after the collision happens. So in example number 4, we have a 40 kg freight car. So basically that's a train car, which is moving at a speed of is costing at a speed of 5 meters per second along a straight track. When it strikes a 30,000 kg stationary freight car and couples to it. What will be their combined speed after impact? So again, the assumption I was making to say the velocities of these particular objects which are involved in this collision, we have to assume that these objects are moving at the same speed, at constant velocity. So the first car weighs 40,000 kgs, is moving at a velocity of 5 meters per second. The other car does not have any motion, but it has got a mass of 300. The person whose microphone is brilliant, Mioba. Can you please switch off your microphone? Brilliant, can you switch off your microphone? So the first car, this one, the 40,000 kg freight car, that's what we're going to denote as the first car, and we denote its mass as M1. So it has got a mass of 40,000 kgs. It's moving with a velocity before they collide. Its velocity, we denote it as U1, the velocity of the first car before collision, and that velocity is 5 meters per second. That's okay. The velocity is 5 meters per second. The second freight car, which is stationary, we denote its mass as M2, and it has got a mass of 30,000 kgs. The velocity of this car, we denote it at U2, and it has got since the car is stationary, it has got a velocity of 0 meters per second. So with this information, we can work out what is the total amount of motion which is happening or which is present before this first freight car collides and couples with the second freight car. So the total amount of motion which is present is given by the total linear momentum. The total linear momentum is a measure of how much motion is happening. That's what linear momentum measures. It measures the amount of motion which is happening. So the total amount of linear momentum before impact is going to be the sum of the linear momentum of these two freight cars. That's going to be the linear momentum of the first freight car before it collides. That's going to be M1, which is the mass of the first car, multiplied by the velocity of the first car before collision, which is U1, then plus M2, the mass of the second car, multiplied its velocity, which is U2 before they collide. So that's going to be 40,000 kgs plus times 5 meters per second plus 30,000 kgs times 0 meters per second. So you can see from here that this total linear momentum is as a result of only the motion which is happening due to the first car. So we end up with 200,000 kgs meters per second. All this motion is as a result of the first car. So this is how much motion is happening just before these two cars, freight cars, couple to each other, before they collide. After they collide, since we are told that these two freight cars, they couple, so they become one, so their combined mass after they couple is going to be equals to M1 plus M2. And since they've coupled, they're going to move with the same velocity. So that way we can work out what is the total linear momentum just after impact. So the total linear momentum just after impact is going to be equals to the combined masses of the two freight cars, M1 plus M2, multiplied by whatever the velocity is, and that's the velocity we are looking for. So the combined mass is going to be 40,000 kgs plus 30,000 kgs multiplied by V, which is the velocity of the freight cars after they have coupled. So that's going to give us 70,000 kgs multiplied by V. So what we have here on top, up here, is the total linear momentum before the cars collide, and what you have here is the total linear momentum just after these cars have collided. Now, total linear momentum, as I've said before, it measures the amount of motion which is there. So conservation of linear momentum requires that just before impact, the total amount of motion which is there should be equal to the total amount of motion which is there just after impact. So therefore, we are required to equate these total linear momentums before impact and after impact to each other. So the total linear momentum before impact, as you can see from what you have worked out here, is 200,000 kg meters per second. This should be equal to the total linear momentum after impact, which is equal to the combined masses of the freight cars multiplied by whatever the velocity is. So we end up with this expression. So this expression we get as a result of enforcing conservation of linear momentum. If momentum is conserved, it means that the total linear momentum before impact has to be equal to the total linear momentum after impact. So from this expression, we can work out what the velocity of the freight cars is after impact by dividing both sides by 70,000 kg. So when you do that, you end up having V, which is equal to 200,000 kg meters per second divided by 70,000 kg, and this is going to give us a velocity which is approximately 2.9 meters per second. So this is the velocity of the freight cars after they couple to each other just after impact. So this is how we use this conservation of linear momentum. Is that clear to everyone? Yes?
Are the rules of significant figures and decimal places not matters in physics?
They do, but I don't really think it's very important.
Okay.
Yeah. Any other question? Okay. Next, we have another example to look at. Here, example number 5. So with example number 5, we have a bullet which has got a mass of 7 grams. So a 7-gram bullet moving horizontally at 200 meters per second strikes and passes through a 150-gram can sitting on a post. Just after impact, the can has a horizontal speed of 1.8 meters per second. What is the bullet's speed after leaving the can? Again, this is a problem of collision. So the bullet collides with the can and passes through the can. So it doesn't stick to the can like in the other example we looked at, but in this case, the bullet actually passes through the can. So this is still a collision problem, despite the bullet not getting stuck in the can. So with this, we can find out how much motion is happening before the bullet strikes the can and how much motion happens after. Now we know the mass of the bullet. The mass of the bullet is 7 grams. We know the velocity of the bullet. It is 200 meters per second. We also know the mass of the can is 150 grams, and we know that the can was seated on a post, so it didn't have any velocity. After the bullet strikes the can, they both have some velocity. The can is starts moving with a velocity of 1.8 meters per second, and we do not know what the velocity of the bullet is. That's what you're looking for. But we can find the velocity of the bullet by enforcing conservation of linear momentum. So we need to work out what is the total amount of motion before the bullet hits the can and what is the total amount of motion after the bullet hits the can. So for us to do this, we are going to denote the mass of the bullet as M1. So M1 is going to be 7 grams. And of course, we do our calculations in kgs. So that's going to be 0.007 kgs. Then the velocity of the bullet before it hits the can, we're going to denote as U1. And that's going to be 200 meters per second. Then the mass of the can, which is 150 grams, we're going to denote it as M2. M2 is going to be 150 grams. And this 150 grams, we need to change it to kgs. That's going to be 0.15 kgs. Then the velocity of the can, which is seated on the post, we are going to denote this as U2. And since the can is just seated, its velocity is 0 meters per second. So it's not moving. So with this information, this is what's there before the bullet hits the can. We can work out what is the total linear momentum before impact. Basically, total linear momentum before impact is a measure of how much motion is happening. What is the sum of the motion which is happening before impact? And the amount of motion which is there is given by linear momentum. So the amount of motion which is there is given by linear momentum, and that's basically what we do here. So we work out the total linear momentum before the bullet strikes the can. So that's going to be the mass of the bullet, m1, multiplied by the velocity of the bullet before impact, u1, plus the mass of the can, m2, multiplied by the velocity of the can, u2, before impact. And this is going to be the mass of the bullet, which is 0.07 kgs, multiplied by the velocity of the bullet, which is 200 meters per second, plus the mass of the can, which is 0.15 kgs, multiplied by the velocity of the can, which in this case is 0. So when we work out when we work out whatever this is, this gives us the total amount of motion which is there before the bullet hits the can. And we end up having this as 1.4 kgs meters per second. So this is how much motion is there. All the motion is as a result of a bullet which is moving at high speed, yes, but it's very small. That's why the motion looks very small here. Now, after the bullet strikes the can, the bullet continues on its journey with a velocity which we do not know, and that velocity of the bullet after it strikes the can, we are calling it v1. Now, remember, we can call this velocity v1 because we are always assuming one thing, to say the velocity of these objects before they collide and after they collide it doesn't change. The velocity is constant. So before the bullet strikes the can, its velocity is always 200 meters per second. After the bullet strikes the can, yes, the velocity can change during that, but after that, its velocity has to remain the same, unchanged, because we are also assuming that there is no other external force which is acting on the bullet just before and after the impact. So in this case, then the velocity with which the can flies off, with a velocity of which 1.8 meters per second, and that's what we're denoting as V2. So V2 is 1.8 meters per second. So with this information, we can work out what is the total amount of motion which is there just after the bullet collides with the can. So that's going to be the total linear momentum after impact. That's going to be the mass of the bullet multiplied by the velocity of the bullet which we are looking for, plus the mass of the can multiplied by the velocity of the can which have been given. So the mass of the bullet is 0.007 kgs, and we are also assuming that in this case we are assuming that the bullet remains intact, so the bullet's mass doesn't change. Then we'll multiply this times the velocity of the bullet after impact, which is v1, and we don't know what this is at the moment because that's what you're looking for. Then plus multiplied by the mass of the can, which is 0.15 kgs, multiplied by the velocity of the can after impact, which is 1.8 meters per second. When we work this out, we end up having a total linear momentum after impact of 0.007 kgs v1 plus 0.27 kgs meters per second. So this is what our total linear momentum is going to be after impact. So what we have up here, we have the total linear momentum before impact. Then here we have the total linear momentum just after the bullet strikes the can. So conservation of linear momentum requires that the total linear momentum before impact should be equal to the total linear momentum after impact. So these two expressions, this one, which is equal to 1.4 kgs meters per second, and this one, which is equal to this, they should be equated. So when you do that, so that's what you have here. This is a total linear momentum before impact. It should be equal to the total linear momentum after impact. So we end up having 1.4 kgs meters per second equals to 0.007 kgs v1 plus 0.27 kgs meters per second. When you get this guy, take it to the other side, you end up having 0.07 kgs v1 equals to 1.4 kgs meters per second minus 0.27 kgs meters per second, and you end up having this 0.07 kgs v1 equals to 1.13 kgs per second. Then we divide both sides by this mass we end up having v1 is equals to 1.13 kgs meters per second divided by this bit. We end up having the velocity of 1.61 meters per second. So you can see that the velocity of the bullet reduces from 1.61 from 200 to 161 meters per second. So the action of the bullet passing through the can basically leads to a reduction in the velocity of the bullet. So it's only during the time when the bullet is passing through the can that there's a force. And that force, like all other forces change velocities of objects. This force is what causes, which basically friction force is what causes this bullet to experience a reduction in velocity. After the bullet comes out from this can, its velocity stays the same. Do we have any questions on this one? Is there any question on how we have applied our conservation of linear momentum to this problem? Okay.
Understand.
Okay, fine. The other bit, which sometimes happens, because usually in cases like this, most of the time, whenever there's a collision, there is always conservation of linear momentum. So whenever a collision happens, linear momentum is conserved. So the total linear momentum before and the total linear momentum after, they have to be the same. However, there are special cases where, apart from just conservation of linear momentum, you can also have conservation of kinetic energy. So when the total kinetic energy is conserved, the total kinetic energy before and after a collision is conserved, then what you have is what is called a perfectly elastic collision. So during elastic collisions, there is conservation of the kinetic energy. Usually, in most cases, that's not what happens. So with example number 6, what we have is a problem where there is conservation of kinetic energy. And if there is conservation of kinetic energy, then what actually happens? So, and I'm sure this is the example we're going to end the day with, because after this we can't add anything else. The only other thing we have to do is tomorrow, where we look at another examples. Okay, so example number 6 reads as follows. Two identical balls collide head-on. If the initial velocity of one is 0.75 meters per second east, while that of the other is 0.43 meters per second west, if the collision is perfectly elastic, what is the final velocity of each ball? So, the first thing is, these balls are going to collide. That's what you're told. They collide head-on. So there's going to be a collision. If there's going to be a collision, then there has to be conservation of linear momentum. The other thing we are told is that this collision is perfectly elastic. What that means is that the total kinetic energy before the collision and the total kinetic energy after the collision is the same. Now, how do we denote these velocities? Because if we have to work out velocities, if we have to work out linear momentum, then we need to know the mass and the velocities. And you've been given the velocities, but except you've been given the velocities with the directions in which these particular motions are happening. The first object you are told is moving with a velocity of 0.75 meters per second east, and the other one is moving with a velocity of 0.43 meters west. So we know east and west are basically opposite of each other. So in this case, it is up to you to choose which direction is going to be positive and which direction is going to be negative. In this example, I have chosen east to be a positive direction. So if I choose east to be positive direction, it means that the velocity which is pointing east is going to be a positive velocity. It's going to have a positive sign. The other one, which is pointing in the negative direction, which is this one, 0.43 meters west, this is pointing opposite of what I've chosen to be positive, west. So the direction in which that particular object is, velocity of that particular object is going to be negative. The other thing to note is that these balls are identical. It means that their masses are the same. If things are identical, then it means that their masses are the same. So the first ball, which is moving east, we denote that as M1. So the mass of the first ball moving east, we denote that as M1. And the mass of the second ball, which is moving west, we denote that as M2. However, we are aware of the fact that these two balls are identical. So basically M1 is equal to M2, and this fact is just going to be denoted as M. So basically we have not been told the masses of the balls, and in this problem it's not necessary to know the masses of the balls, as it's going to become very apparent. Okay, the mass of the the velocity of the first ball, which is moving east, since we choose east to be the positive direction, we choose east to be positive, then it means that the velocity of the first ball is going to be denoted with a plus sign, a positive sign. So again, to write it as U1 is equals to plus 0.75 meters per second. This is before impact. Then the velocity of the second ball, which is U2, is going to be written as minus 0.43 meters per second. The reason why it is minus is because we have chosen east to be positive direction. If east is positive, then west is opposite of east, then west is going to become a negative direction. So we know that the balls have got identical masses. Whatever the mass is, the actual value of the mass we don't know, but what we know is that the masses of these balls are the same. We also know the velocities of these balls. One is plus 0.75 meters per second. The other ball is minus 0.43 meters per second. So with this information, we can work out what the total linear momentum is. How much motion is happening as a result of these balls moving in these directions. So that is going to be the mass of the first ball multiplied by the velocity of the first ball before impact, plus the mass of the second ball multiplied by the velocity of the second ball before impact, which is U2. However, like we have said, these balls are identical, and what basically that means is that M1 is equal to M2, which is just M. So here M1 plus U1 plus M2, M1 multiplied by U1 plus M2 multiplied by U2. This is just going to be equals to M multiplied by U1 plus M multiplied by U2. So we end up having, when we factor out the M, since M is the same, we end up having M equals to M multiplied by brackets, open brackets, U1 plus U2, close brackets. So that is how much the linear momentum is. That is before they collide. After they collide, since it's a head-on collision, the first ball will have to bounce back, and the second ball will have to bounce back. So the first ball, which was moving east, has to bounce, it will have to move west. The second ball, which was moving west, it will have to bounce back, it will have to move east. So after they collide again, these two balls are going to have different velocities. So with that being the case, this bit here, we'll skip it a bit for now, we'll come back to it later. So we can also similarly, the same way we have done here, we can work out the total linear momentum after impact. So the total linear momentum after impact is going to be equal to the mass of the balls, which is M, open bracket, then the velocities of the balls after impact. That's going to be V1 plus V2. V1 is the velocity of the first ball after they collide, then V2 is the velocity of the second ball after they collide. So this bit here is the total linear momentum after impact. This other bit we have here is the total linear momentum before impact. Since this collision, there is a requirement that the total linear momentum before impact and after impact should be the same, as in conservation of linear momentum. So we end up having this expression here. M open bracket U1 plus U2 is going to be equals to M open bracket V1 plus V2. We have got an M on both sides here and there, so the M's are going to cancel out. So when they cancel out, you're going to end up with this expression here, U1 plus U2 equals to V1 plus V2. Now remember, we know what U1 is, we also know what U2 is. What we do not know is what is V1 and what is V2. So we can substitute the values which we know in this expression to make things a bit easier. So when you do that, you end up having V1 plus V2 is going to be equal to U1 plus U2. Now U1 is the velocity of the first ball. Since the first ball is moving in the east direction, it's going to be plus 0.75 meters per second, plus the velocity of the second ball, which is going to be moving westwards, is going to be minus 0.43 meters per second. So we end up having this expression V1 plus V2 equals to 0.32 meters per second. We can, since you want to come up with an equation, you end up having this V1 plus V2 equals to 0.3. Now, with this does not tell us what the velocities of the first ball and the second ball is. We still do not know what V1 is. We still don't know what V2 is. However, we know how V1 and V2 are related now. We know that if you add V1 and V2, what you get is 0.32. That's what we know. So this is what we get from doing conservation of linear momentum. In this particular example, since we do not know the masses of these particular objects, things are not so straightforward. So the other thing we need to do is, we are told that the collision is perfectly elastic. Now, when you have got a perfectly elastic collision, what it means is that the total kinetic energy before the collision happens and the total kinetic energy after the collision happens, these have to be the same. So we can work out, now that we know that the velocities of these balls before they collide is U1 and U2, then after the collision is V1 and V2, we can use this information to work out the total kinetic energy before collision and also work out the total kinetic energy after the collision. So the total kinetic energy before collision, that's what we're working out here. The total kinetic energy before collision, starting from here. So it's going to be half m1, the mass of the first ball, multiplied by the velocity of the first ball, u1 squared, plus half m2 multiplied by the velocity of the second ball squared, u2 squared. This is the total kinetic energy before the collision happens. Now we know that the masses are the same. So if the mass is the same, if m1 is equals to m2, we can obtain a simplified version of this expression. So that's going to become equals to basically half m, then u1 squared plus u2 squared. So basically the m, which is the same, we can just factor it out and half. So we end up with this. So this is the total kinetic energy before these two balls collide. After finding out the total kinetic energy before these balls collide, we can also in similar fashion work out what the total kinetic energy is after the balls collide by following the same thing we have done here. So the total kinetic energy after the balls have collided, that's what we have here. So this is going to be half m1 multiplied by v1 squared plus half m2 multiplied by v2 squared. And since m1 and m2, the masses are identical, so we end up having a simplified version of this expression as half m v1 squared plus v2 squared. So this is the total kinetic energy after the balls have collided. So since the collision is elastic, like I've been mentioning, it means that the total kinetic energies before and after collision, they have to be the same. So you equate this expression of kinetic energy after the total kinetic energy after a collision and the total kinetic energy just before collision, this one here. So we have to equate these expressions. So when we equate these expressions, what we end up with is this. So you end up having, we end up with this here. So this bit here, this side is the total kinetic energy before collision. This should be equal to the total kinetic energy just after collision. And as you can see, there's a half m here and half m in front. So if you cancel out the half m, you end up with only u1 squared plus u2 squared is equals to v1 squared plus v2 squared. Now we know u1 and u2, so we can substitute the values of u1 and u2 in these expressions. So you end up having So this bit we still do not know. V1 squared plus V2 squared we still do not know. So we end up having this. So V1 squared plus V2 squared is going to be equals to open bracket plus 0.75 meters per second squared plus open bracket minus 0.43 meters per second squared. That. So when you work out this, you work out this whole thing here in here squared plus this whole thing in here squared. What you end up having is V1 squared plus V2 squared equals to 0.7474 meters per second squared. This. When you drop these units, you end up having V1 squared plus V2 squared is equals to 0.7474. So basically, this is what you end up with. So we now have two equations. There's one, which we have, this one, V1 plus V2 is equals to 0.32. Then we have got this other one here. V1 squared plus V2 squared is equals to 0.7474. So these two equations we can solve using different methods. You can use simultaneous equations. But what we're basically going to do is you're going to use the first equation, which is this one. V1 squared plus V2 squared equals to 0.32. We're going to rewrite this first equation as follows. We're going to write it as V2 is equals to 0.32 minus V1. After rewriting the first equation like this, we are going to substitute for V2 here, there where I've highlighted. We're going to substitute there so that you only remain with V1. Then we work out whatever it is. We find what V1 is. Then after that, later on, we find out what V2 is supposed to be. So when we do the substitution, when we substitute in this expression for V2, so we end up having V1 squared plus open bracket 0.32 minus V1, the whole thing squared, equals to 0.4747. So next you expand this. When you do the expansion, this is what you have, like that and like that, equals to 0.7474. Then you try to simplify this. You make this whole thing expand, so you end up having V1 squared equals to 0.32 squared minus this whole thing here, like that. And when you simplify this, you end up having 2 V1 squared minus 0.64 V1 minus 0.645 equals to 0. Now, when you look at what we have here, just a minute, I'm trying to see if there's someone admit. Now, when you look at what we have here, this thing which we have here, this new equation which you have here, looks very similar to, I'm sure, an equation you have seen before. It looks similar to this, which is ax squared plus bx plus c is equal to 0, which is a quadratic. So in this case, if this is a quadratic, then it means that our a, in this case, our a is 2, our a is 2, our x is v1, our b is minus 0.64, our c is minus 0.645. So basically, our x is v1, our a is 2, our b is minus 0.64, our c is minus 0.645. Since this is a quadratic equation, we can use the quadratic formula. X is equal to minus b plus or minus the square root of b squared minus 4as divided by 2a. And when you substitute, we end up having this v is equal to like this. So this is where the substitutions have been made, plus or minus the square root of that thing here, which is the b, then minus 4, this is the a, then the c, then divided by 2a. So the whole thing end up having v1 is equal to 0.64 plus or minus the square root of 0.409 plus that and this. So you end up having v1 is equal to 0.64 plus or minus 2.36 divided by 4. So you end up, basically what you are looking at here is that mathematically, after the collision happens, there are two velocities for the first mass. So that's going to be v1 is equal to 0.64 plus 2.63 over 4, or v1 is equal to 0.64 minus 2.32 divided by 4. When you work out this, you end up having v1 is equal to 0.75, or v1 is equal to v1 is equal to minus 0.43. Now, this v1 is equal to 0.75. Basically, that is v1 is equal to 0.75 meters, and v1 is equal to minus 0.43. Now, mathematically, these solutions are fine. If you're doing mathematics, then the solutions are fine. But you're not doing mathematics. What you're doing is physics. And if you look at this first solution here, it's positive. Okay? It's positive and it's 0.75. We know that the first mass had a velocity of 0.75. So the first answer here, V1 is equal to 0.75, is telling you to say, when this mass collides with the second mass, its velocity does not change. It just passes through the second mass, the second identical mass, and continues moving eastwards. That's what the first velocity 0.75 is telling you. To say, the first mass, after collision, continues to move east. It passes somehow, it behaves as if the second mass is colliding with doesn't exist. It's like it's passing through thin air. Now we know this is not possible because these masses are actually, identical masses are actually made of matter. And if you're going to collide with something, you have to bounce. So the first solution of 0.75 meters per second does not make sense. Are we clear? V1 equals to 0.75 meters per second does not make physical sense because it's not possible for the first mass to collide with the second mass and continue moving eastwards as if nothing has changed, as if nothing has happened. Are we clear?
Yes, sir.
However, the other answer, V1 is equal to minus 0.43 meters per second, says something. It says that the first mass collides with a second mass, then it bounces back, starts moving westwards. That's what the negative is telling you. The first mass collides with the second mass, it bounces back, and it starts moving backwards towards the west. Now, this is exactly what we expect. However, there is actually something else which is happening. If you look at the velocity V1, the velocity V1 is actually the velocity which the second object, which was moving in the west, had. The velocity of the second object, we wrote it as U2, and if you look up here where we are coming from, U2 is minus here. U2, the velocity of the second mass, U2 is minus 0.43 meters per second. So after they collide, because these particular objects have got identical masses, after they collide, the first mass moves backwards towards the west with the velocity of the second object. That's what you have here. The first mass bounces against the first mass, starts moving west, and it moves west with the velocity of the second object. So the first object obtains, after collision, it obtains the velocity of the second object. If the first object obtains the velocity of the second object, that's what makes sense because it's moving in the right direction. Then what happens to the velocity of the second object after collision? What happens to V2? So this bit here, V1 equals to 0.75 meters per second, doesn't make sense. However, V1 equals to minus 0.43 meters per second actually makes physical sense because the ball is moving in the right direction. And we are being told here that it moves backwards, westwards with the velocity of the first ball. What happens to the other ball, which was moving westwards? So we can try to work out V2. So V2 is going to be 0.32 minus V1. Now V1, we know, we have found V1 to be minus 0.43. So V1 is, if V1 is minus 0.43, then we can work out V2. So V2 is going to be equal to 0.32 minus 0.43, and this gives us a velocity of 0.75. So we end up having V2 as having a velocity of 0.75 meters per second. So the second mass will bounce against the first mass, and it will move east. But as it is moving east, it is going to move east with the velocity of the first ball. So what actually happens here is that, as you can see, these two identical balls exchange velocities. Are we clear? The two balls, before they collide and after they collide, when they collide, they exchange velocities. The reason why they are able to do that is because we have enforced a requirement that the energy, or the energy before, the total kinetic energy before collision and the total kinetic energy after collision have to be the same. Are we clear?
Sir,
Yes.
for instance, we are having an exam that requires you to show your working, and then due to what you've explained here, they ask a similar question. Would you be given full marks if you were to just basically write the answer, since you apply,
if you know, then you just write what the answer is.
but you don't have to show the working, since
No, you will not be required to show the working because there are too many. Your exam is going to be have a multiple choice.
I'm saying, for instance, take an instance, let's say if it was possible to revert back and we had such a question in an exam like that, where we have to show the working.
You have to show the working then. You have to show the working. If you are required to show the working, then you have to show it. But as you can see, this question is a bit it's a bit more difficult, because it does not just involve what is conservation of linear momentum, but it also involves conservation of kinetic energy. So if he's going to do conservation of kinetic energy, then somewhere, somehow, there will have to be a quadratic equation. So that's what makes it a bit more difficult. But we have used this equation to demonstrate something, to say when there is what is called an elastic collision, there's just going to be basically an exchange of velocities. There is an apparatus, something called a Newton's Cradle, an apparatus which exploits this same thing, conservation of forces, conservation of linear momentum, and also conservation of kinetic energy. Let me just look for a video on YouTube so that you can see what happens. Okay, this video is just a short video. It's about 4 minutes. So I'm going to stop sharing, and I'm going to go share a YouTube so that you can see what we mean exactly with what we have just demonstrated there. So there's a piece of apparatus called Newton's Cradle. Can you see my YouTube?
Yes.
Okay, so yeah, so basically this is one of the advantages of online. We can even go to YouTube. Okay. So these things are going to be exchanging velocities basically. So what you're seeing is an exchange of velocities. So you start with 2, 1, then 2, like that. As you can see, this thing is only possible because the balls are identical. So there has to be a requirement that the balls should be identical. And that's what you see there. Okay, so basically we stop there, and like I've said, this exchange of velocities, where things collide, two identical masses collide, then they exchange velocities as has been demonstrated here, is only possible because one, these masses have to be identical, and two, you have to enforce conservation of linear momentum and also conservation of kinetic energy. Are we clear? So you can check out more videos on how this happens on YouTube, but basically that's what I wanted to show you, to show that with the example we have looked at, this whole thing of exchanging velocities does actually happen. Okay, unless there's any question, we come to the end here for today. We still have a class tomorrow. Yes.
When the balls have identical masses and different velocities, so is there any probability of them to have different values with those we have?
No. What is there? What?
I'm saying those values we have obtained.
It only works that way because the masses are the same. They have to be identical. If they're not identical, then it's not going to work. Yeah. Any other question?
Sir.
Yes.
Sir.
Yes.
Angular moments would it be the part of the quiz or what?
Which what?
Angular moments.
Angular moments.
Would be included in the quiz
When is the quiz?
on Friday.
I don't know. What have you seen? What topic is there for the quiz?
Angular, you said linear momentum. How about angular momentum?
No, angular momentum can only be done. You can only look at angular momentum after you have started looking at motion in a circle. So after this topic, we start looking at motion. You start with the other professor next week. You start looking at circular motion. Then after you've done circular motion, that's only then can you start looking at angular momentum and stuff like that.
Okay, sir.
Yes. Okay. Is there another question?
Sir, which professor are you handing us to?
Professor Calera. You will be doing your things online also. He lives in the UK because of the coronavirus. So you'll be taught from the UK.
Alright, sir. Thank you.
Okay, have a good night.
Now we wanted you.
Yes.